Hello. Hello. Can you hear me? No. Hello. Well, hello. That's my name. You can call me Kai. I'm here to present System F omega with equirecursive types for data-type-generic programming. This is joint work with Paulo Jaruso and Klaus Ostmann at the University of Tübingen in Germany. This is the bird eye overview of the talk. There are many ways to view a data type, and many of those ways are actually useful. In data-type-generic programming, however, one often gets locked into one single view, and it is not so easy to apply these wonderful abstraction techniques in generic programming to all the other views on a data type. And what we did is that we designed a calculus with equirecursive types so that we can investigate this problem and propose a solution for it. The problem we call the tyranny of the dominant functor, and we will see why it is called in that way. This is the outline of the talk. Data-type generic programming provides the context, the background for our investigation, and it is the environment in which we state our problem. The solution we propose as a language is System F omega with a bunch of extra features. And we'll also talk about consequences for considering such a language. OK, this is the background. We are going to walk through the standard example of fold so that everyone is on the same page. On the left side, you see a definition of syntax trees of lambda calculus in a Haskell-like language. On the right-hand side, you see a function to compute the free variables of lambda terms. The idea for data-type generic programming is that the programs operating on a data type resemble the definition of the data type. So what do we mean by that? What do we mean by that? First, in free variables, every constructor of the data type gets turned into an operation. The variable constructor gets turned into the singleton list constructor. The abstraction constructor gets turned into a filter operation. And the application constructor gets turned into list concatenation. And the type recursion becomes recursive calls at the term level in the program. The recursive occurrence of term inside the body of abstraction become a recursive call on the body of the abstraction. And the two recursions, the two appearances of term as the operator and the operand of applications, they in turn become recursive calls on the operator and operands of an application. This is all very good and well. We can abstract this by writing down the definition of term in a different way. In terms of term f, this is commonly called the pattern functor of a data type. And the data type term itself is rewritten as a fixed point of this pattern functor. What's cool about this is that we can now, from the description of the pattern functor, generate generic traversals on the data type. For example, the fold right here. And now the operation-specific parts can be provided by the users in an algebra. That's all good and well, but the problem is there are multiple meaningful ways of traversing a data type. Here, we see another function on terms. It is a function that computes the list of arguments in the top-level application tree. We might want to call this function, for example, in a eval apply compiler, for example. We want to know what the arguments are, whether there are enough arguments to fully apply a function. Now, here at the operator position of applications, we still have a recursive call to the arguments function. However, in the other two type recursions, there is no corresponding recursive call at the term level. The worst case is in the argument. Oh, sorry. The worst situation happens, in fact, at the at the operand position of applications, in that the term occurs naked within the body of arguments without a recursive call around it. Okay? So if we really want to refactor the args function in terms of fold, then we will have to define the pattern functor in another way. In particular, the type parameter of the pattern functor cannot occupy the position we do not want to descend into. It cannot be here, and it cannot be here. Therefore, we have to replace those positions by a constant type. In this case, the type for the lambda terms themselves. Now we have a problem. If we want to write a compiler that does static analysis at the same time, we want to get both the free variables of a term and we want to get the arguments of it. Now we have a problem because each of these can be refactored in terms of fold, but after doing this refactoring, their types become incompatible. If I want to write a program like this with generic programming techniques, then the program is ill-typed. That's the problem. There are isomorphism between all those different types, and they are in fact defined to model the same problem domain, the syntax trees of lambda terms. However, they are only isomorphic, and they're not equal. They're not compatible. And the difference lies only in the way we want to traverse them in the future. There are other ways to imagine how we might define lambda terms, like this one. This one only descends 2 levels at a time, and even more complicated ways of structuring this data. This one descends into the operator position 2 times before starting the recursive traversal. So here is the problem of the tyranny of the dominant functor. Either free variables or args can be written in terms of fold, but not both. And which of them can be refactored depends on the representation of term. That is assuming we want to write a well-typed compiler in the first place. And the idea of a solution is to turn all these isomorphic types and turn them into equal types. And we are going to make this precise by defining a formal language called f omega mu. We define this language to discuss data-type-generic programming, so of course we want to represent data types. And what features do we need for to represent data types? We need type-level recursion. That is represented by this type-level fixed-point combinator mu here, and the type-level function represented by this lambda tau. The tau occupies the recursive positions of lambda terms. Inside one constructor, we can have multiple fields, so we need some kind of prototype. For this work, we are using record type. So the bodies of the abstraction and its parameter are encoded by a record with field x and body, respectively. Similarly, the operator and operand of an application encoded in this record with 2 fields. And finally, since there are multiple ways of constructing a term, this choice is represented by the variant type here, denoted with angle brackets. Now this notation is kind of standard. It's in the Types and Programming Languages book by Benjamin Pierce. What other language features do we need? We want to be able to have folds in the language, so we will also need polymorphism and type level application. That's the result. On the left, we have the language features that are already in system F omega. There are type functions, type level applications, and polymorphism. On the right-hand side, we have features put in to support generic programming. They are type recursion, recurse, and variance. Okay, how does that solve our problem? In the same way we can represent term as in the new calculus F omega mu, we can represent term 1 and term 2. Those are the decompositions for free variables and for getting a list of arguments. Okay? So for free variables, it looks exactly like the definition of term. And for the, this one is for the free variables. There are recursions at all subterm positions. And this one is for getting the arguments. Recursion happens only at the operator position. And now they are equal in the new calculus. How do we do that? You get the idea. How do we do that? We do that by imagining types as infinite trees. In particular, we interpret the fixed point combinator as this infinite tree, lambda f dot f, calling itself an infinite amount of times. What do we gain from that? We gain the equality mu f equals f of mu f. Okay, how does that apply to our situation, to our need to equate term 1 and term 2? Well, let's start the expansion. Let's start with the definition of term 1. It's a mu type, and we expand once into a variant var f's app, followed by a string inside var, the parameter and the body inside abstractions, and function and argument inside applications. The parameter position A gets replaced by the recursive types itself. That is what this type looks after one step of expansion. And we can do this recursively an infinite amount of times to get this tree. It is self-similar. The parts of this tree looks like itself. Okay? And this tree, this infinite tree, is exactly the tree we're going to obtain if we expand the second representation of term to get a list of arguments. How does this work? Well, after one expansion, we get something like this. Because the constant positions, they are already pre-expanded into the infinite trees that is kind of wrapped in the other term representation. So all we need to do is to descend into the argument position and expand further there. Okay? Now, let's see both expansions in parallel. 1, 2, 3, 4. I hope this is convincing enough that we actually get equal types for the two term representations. Now we have achieved type equality, and our compiler becomes well-typed, so the tyranny is ended. The tyranny has ended, right? Yeah. What can we use this for? Well, all these different representations of terms become equal types, and we can use them to generate different traversal combinators in generic programming. We can generate fmap and fold and traverse. They can all interoperate on the same data as we may want to do. Yeah, so one term representation can generate multiple generic traversal combinators, and for each generic traversal combinator, we can generate it from different representations of the same data type. So are we done here? Did we win? Reviewer A has the following to say. Once you've decided to throw arbitrary unrolling of fixed points into the language of types, the toothpaste has escaped from the tube, and you have to resort to extreme cleverness to put it back in again. So what is the toothpaste, and why do we want to put it back? Well, two things come under question. The first one is type soundness, and the second one is decidable type checking. We have enlarged the typing relations, so now more terms become well-typed. How can we be sure they do not get stuck during evaluation? And moreover, how can we decide whether a program is well-typed in the first place? Well, for type soundness, we have a satisfactory answer. The full system f omega mu is type sound. But for decidable type checking, we can only obtain this result for a fragment of the calculus. Which fragment? In full f omega mu, we have the fixed point combinator at the type level for all the different kinds. We can expand them to star, star to star, and so on and so forth. It's an infinite set of different type level fixed point combinators. And in the decidable fragments, we're going to throw away all of these to have only the rank 1 fixed point combinator left. The advantage of doing that is then the Berarducci trees of types in this fragment become regular trees. They are self-similar. The number of distinct subtrees in those infinite types become finite, so that the problem of type checking become tractable. We'll look at the details later. We'll look at the details now. The type checking algorithm for the decidable fragments start with a type checking algorithm for f omega that is also documented as standard in the types and programming languages book. It relies on an equality test on types, which is just beta equivalence for simply typed lambda calculus, because that's the type level language for f omega. And that can be done by normalization. However, after we add fixed point combinator to the language, even for the rank 1 situation, the types become infinite. And and we cannot just normalize. So what do? First, we normalize those types, leaving the fixed point combinator uninterpreted. And then the result is a finite description of a regular tree, so that we can use this Pierce's version of Amadio-Cadelli algorithm to check whether those trees are equal to each other. The correctness of this algorithm is not trivial and needs justification. And for soundness, we also follow the architecture of the standard soundness proof for f omega. It relies on the confluence of the type level language, simply typed lambda calculus in the standard case. After adding fixed point combinators of arbitrary rank to the language, the type level language becomes infinitary lambda calculus, and we will have to rely on a confluence proof of infinitary lambda calculus. What we use is the co-inductive proof by Luca, and the hook here is actually pretty deep. Like, we are using the lemmas used in that confluence proof to obtain properties that we need. All right, so half the toothpaste is back in the tube. What should we do now? Should we try to come up with a type checking algorithm for full f omega mu? Well, this is something I learned this Monday in the higher order model checking tutorial, and it's not in the paper, but should have been. These are 3 closely related problems. The first one is equality test for higher ranked recursive types. The second one is the equivalence of higher order recursive schemes. They are like recursive schemes for functions calling each other, but if we lift it to the type level, we can imagine them as mutually recursive types. And the third problem is the Böhm tree equivalence of lambda y calculus, which is just PCF without the primitive operations, without arithmetic, without Boolean operations, and so on and so forth. And in higher order model checking, the equivalence of high order recursive schemes is a long-standing and well-known open problem. So we don't have really any hope for solving that anytime soon. And as a consequence, we don't even know whether PCF remains Turing complete if we remove arithmetic from it. Review A kindly suggested a workaround to this very hard problem, to this unknown decidability problem. And the suggestion is that we ask the programmer for help. We can start with an iso-recursive source language with decidable type checking, and then we ask the programmer to provide equality proofs for the kind of type equality needed to make their programs well-typed. And then we compile them into an equirecursive intermediate language, which will be well-typed by construction. This way, we get the part of the benefits of both worlds, both isorecursive and equirecursive types. In the paper, we will, there are more descriptions about the tyranny of the dominant functor, which we have seen, and the formal definition of system F omega mu, which we also have seen, kind of. And in the technical report version, there are the full proofs of soundness and decidable type checking for a fragment, and a logical relation that generates traversable functors given a description of a data type. Why do we care about traversable functors? Because it's kind of the most generic programming combinator of the three. The other combinators can be defined as instances of traverse, and as well as many other popular combinators in library, like GMAP-T in the Scrap Your Boilerplate, for example. That's all.
Hi, Peng Wang from MIT. It's an interesting problem. So my question is, it's an obvious one. How large is the decidable fragment you came up with? And does it cover all the applications you are interested in?
The question is whether the decidable fragment of F omega mu cover all the applications I'm interested in. Unfortunately, it does not. With only the rank 1 fixed point combinator, we can now express nested data types and GIDTs, which are obviously useful. However, it covers all the regular data types. So although it's not all the use cases that we want to support with generic programming, it's a significant portion of that. It's the easy portion of that, so to speak.
Thank you.
It's me again, sorry. I just wondered, when I saw your problem at the beginning was you had an isomorphism, but you really wanted to have an equality, right?
Yes.
I don't know, this is exactly what univalent type theory gives you, right? So I wonder whether in this setting, this problem would just disappear.
The question is whether by using univalent type theory, the problem disappears.
Yes.
The problem between type isomorphism and type equality disappears. No. That is a good question. I don't know the answers right now. For this particular case, the type equality proofs are actually co-inductive, so they are infinite. I'm not sure how well univalent type theory can support such cases at this very moment.
I don't know.